Going? Uh-oh, where's my... Right. Okay, so here is the deal then. So what we're going to learn about today, honestly, there's not a whole lot that's new here. We're just going to formalize a few things that we've talked about and just sort of work a little bit more with free body diagrams, okay? So free body diagrams we've been making them all along. It's a drawing of your object with all of the forces labeled on it. And then usually off to the side you write down your acceleration and your net force. And then if you know anything about your velocity, you usually write that down, okay? So that's kind of what we're going to work on today. And in specific, we're going to learn a little bit more detail about normal force, which we've talked about, and another force called tension. Okay, so that's kind of the deal for today. All right, so this basically just says what I said a second ago, which is that your drawing is going to include, for sure, it's going to include your net force and your acceleration, kind of written off to the side. And then if you know anything about your velocity, you're going to kind of write that down nearby too. Okay. Notice when you make your free body diagram, you have to literally draw the object with all of the forces on it. Okay. So every force is going to get its own arrow. Okay. So anyway, like I said, we've been making drawings like this for a little while. We're just going to fill in some details. All right. So like I told you guys, I've been telling you guys for the last, 4 or 5 days or so. Remember, there are 2 ways to find acceleration and 2 ways to find net force, right? You can find net force by doing Newton's second law or by using the definition, which is add up all of your forces, okay? And then you can find your acceleration by using Newton's second law, or by using one of those equations from kinematics, A equals VF minus VI over T, or, all those equations that we had on the last test. So that's sort of what ends up happening, is as you do these free body diagrams, what always ends up happening is it's sort of like doing one of those, what are they, Sudoku? I can never say that word. One of those puzzles where it's sort of like, what do I know, and how can I use that to get the thing that I need to get, you know what I mean? So that's kind of the idea here, is you're going to have, your diagram, and either you'll know all the forces, and you'll use that to find your net force, or you'll be missing a force, and you'll have to find some other way to find your information. So anyway, this kind of walks you through the different processes. In general, if you know the acceleration, then use Newton's second law to find the net force. And then once you've done that, you can use the definition of net force to find some missing force. All right, and then the other type of problem is one where you know all of the forces, and then you'll use this equation to find your net force, and then this guy to find your acceleration. Okay, so a lot of it is just sort of, what do I know? All right, so let's do some examples here. We're going to start out with some super, super basic examples, and then they do get more difficult, okay? And then later this week, we're going to do friction. We've already talked a little bit about friction, but we're going to learn more formally how to calculate friction. And that's when the difficulty really ramps up. All right, so here we go. In this first example, we've got a 6-kilogram cat named Gordon jumping out of a tree. So we're going to make a free body diagram for the cat while he is falling. So draw a cat. And I'll be honest, you guys, most science teachers will tell you to just draw a dot for the object. I like drawing cats, so so there you go. All right, so there's our cat. So what forces are going to be acting on him? Gravity. That should always, from this point forward, every single free body diagram you draw, you're going to always start by identifying the mass and the force of gravity. I will always give you one of those 2 things, and then you use whichever one I give you to find the other, right? Because we know Fg equals m times Ag. All right? So this one time I'm going to write out the calculation. From this point forward, though, I'm going to expect you guys to know how I do this. All right, so the mass is 6 kilograms. Acceleration of gravity is negative 9.8 meters a second squared. Multiply it out, and you get negative 58.8 newtons. There's our force of gravity. So, any problems with how I found the force of gravity? What's another word for force of gravity? Weight. Very good. Okay, so are there any other forces on the cat besides gravity? Okay, air resistance, if there is, we are, as I said earlier, going to, unless I say otherwise, we're going to ignore air resistance. Okay, I don't think I said that today, but I know I've said it in the past. All right, so I think that's it. So now we can find our net force. So what's the net force going to be, you guys? Just negative 58.8, right? This is the only force on the cat. So our net force is that force. And then our acceleration is just going to be negative 9.8, right? All right, so here's our drawing. This is sort of a complete free body diagram right there. Notice I didn't write anything down about the velocity here because I don't know what his initial velocity was. I don't know how fast he's moving at the instant I've pictured, but the entire time he's in the air, this is what my free body diagram is going to look like. Cool? All right, so now what have we got this? We've got Roy holding a box in his hands. So the free body diagram is for the box, not for Roy. So here's the box. The mass of the box is 14 kilograms. So start by finding your force of gravity. So 14 times 9.8 is a number that if I had been smart, I would have figured out in advance. 14 times 9.8 is negative 137.2 newtons. All right. Are there any other forces on the box besides gravity? Yeah, Roy, right? Roy is holding it, right? Now, because he is, I guess it doesn't explicitly say it, but we can assume he's holding it at rest, right? Okay, and so the idea is it's at rest, which means that my acceleration is 0, which means that my net force has got to be 0. So I can now figure out what the force of Roy has to be. How much force does Roy need to make our net force 0? 137, right? Technically what we're doing here is we're saying x, force of Roy, plus negative 137.2 equals 0. And then solving that, right? I'm not going to write that all out, though, because it's obvious that this has to be 137.2 newtons, right? Hello? All right, so that's just this. He's holding a box at rest in his hands. Gravity's pulling down, he's pushing up. Easy peasy, yeah? Pretty good? All right, cool. All right. Next example. 14 kilogram box sits at rest on a table. Look, you guys, it's the same thing. Right now, there's two forces on the box that I'm holding here, the water bottle. Right? Gravity's pulling it down with whatever it was, 137.2 newtons. My hand is pushing it up with 137.2 newtons, right? The only difference is when I set it on the table, now instead of me pushing it up, it's the table. Okay? Now, up until now, we've just referred to that as the force of the table. Now we're going to give that a more formal name. That's called the normal force. All right? The support force provided by some sort of inanimate surface that an object is sitting on is called normal force. All right? It will always act in a direction that is perpendicular to the surface. Okay? So we will see a clearer example of that in a minute. In math class, you might have talked about the normal line. A normal line is, by definition, perpendicular to the line or the path that it's intersecting. So that's where that comes from. All right, so anyway, so here's our drawing. Here's your box. The mass is 14 kilograms. Gravity's going to pull it down with negative, what was it, 137.2? Again, it's at rest. Therefore, my acceleration is 0. My net force is 0. So I've got to have a normal force of 137.2, right? Oh, thank you, sir. All right. Is everybody good with the normal force problem? All right. At this point, this seems like a really simple idea, but it's totally something that messes people up. So let me say a couple things. First of all, it doesn't always point straight up. Okay? It does as long as it's sitting on a flat horizontal surface. Okay? And here's the thing that messes people up. It doesn't always equal the force of gravity. All right? In this example, it does, because the only two forces are gravity and the normal force, the table. Okay? But we're going to see as we go through these examples today that sometimes your normal force is bigger than the force of gravity, sometimes it's smaller than the force of gravity, sometimes there is no normal force. All right? So you really need to make sure that you're thinking about what's going on. So are there any questions before I go on? Okie dokie. So this one's a little weird. To be honest, I probably should have waited on this example until after we'd formally talked about friction. It's there's not, I guess, a whole lot going on. All right, so it says Sally pushes a 3-kilogram painting horizontally against a wall with a force of 50 newtons to prevent it from sliding down the wall. Make it through my diagram. So it's this. There's a painting. She's holding it against the wall. Okay? So let's draw that. So here's the wall. Here's the painting. The problem tells us that the painting has a mass of 3 kilograms. Remember, first force I always, without exception, want you to draw is your force of gravity. So we can go ahead and put that in. Force of gravity is going to be 3 times 9.8, so you get negative 29.4 newtons. All right, so that's always your first step. Second step, draw any forces that are explicitly given to you in the problem. So does this problem tell me explicitly any forces? Yeah. Tells me Sally's force, right? Everybody point for me. Which way is she going to push? This way, right? Because she's pushing the painting against the wall. So put that in your drawing next. Force of Sally is, and the way I have it drawn, it's going to be negative 50 newtons. Now, you may have flipped your drawing around and had her pushing, maybe your wall was on the other side of the room. All right, so those are my only 2 forces, right? Those are the only ones that I know without making some inferences, right? So now, this is the hard part. After you draw your force of gravity and write down everything you know, you got to think. I don't mean that in a mean way, but I just at this point, it's not cookie cutter. You really need to do some problem solving, okay? So what else do we know? There are a couple other things we know sort of about what's happening with the painting. Sure, give me one thing, Zach. Very good. Yeah, the painting isn't accelerating, right? It's just staying at rest. Oh, I know the acceleration. That means I can use Newton's first or second law to find the net force. What's the net force got to be, you guys? 0, right? So this means that I have to have some other forces. I need to have at least one more force that cancels out gravity and Sally. Okay, what do you got, Connor? So let's think about what's going on. I'm gonna push you a minute here, Connor. All right, so here's the deal, right? All right, so we can see gravity's pulling the thing down, pulling the picture down, and I'm pushing it against the wall. So let's talk about me pushing it against the wall, or Sally pushing it against the wall. Something is preventing the painting from going that way. The wall, right? The wall is supporting the painting. It's preventing the painting from going that way, right? So what's the name of that force? Normal force, right? Okay, so we know there's got to be a normal force, and we know how big it's got to be. How big does it have to be? 50 newtons. It's exactly enough force to prevent the painting from going through the wall. All right, that's how I'm going to describe normal force very frequently. Is I'm going to describe it as it's providing just enough force to prevent your object from going through whatever the surface is. All right, if this wall was made of Jell-O, then the Jell-O wouldn't be able to provide enough force, and I could, right, push the painting into the Jell-O, right? And it would make a very satisfying slurping sound. All right, are we good with what we've got here so far? Sorry if that was disturbing. All right, are we all good with this? Yeah. All right, now there's one other force. For some reason, the painting isn't sort of falling, and I'm going to choose this word specifically. It's not sliding down the wall. Friction. Friction is preventing. Look, if I don't push hard enough, it starts to slide. Okay? So when we talk about friction, we'll learn sort of how that works. But yes, that is correct. This is friction. How much force does it have to be? 29.4 newtons, right? Does that make sense, you guys? Notice, friction is opposing the attempted motion, right? If friction didn't do anything, it would slide down the wall, and friction is working against that by pushing up. All right? I'm going to put a little S here next to my force of friction. When we do friction, we're going to learn there's two types of friction, static and kinetic. I'm just putting the S there now so that later on when you're studying for your test, you'll see that S and you'll be like, oh, I know what that is. Okay? So we'll learn in a couple days why that S is there. Cool? All right, any problems with this example? All right, couple things. Notice, normal force doesn't point up. It's pointing sidewaysy. And it's not equal to gravity. Okay? So that was why I wanted to start with this example. Right? All right, now, we got this. A 12-kilogram dog is sitting on the ground. So here's the ground, here's a dog. I can't draw dogs. Why did I choose a dog?
What is that? What's that?
It's a dog.
It's a dog.
He's got like floppy ears and...
Better is better than anything I do.
All right. I don't know if it's better than anything you do, but...
Oh.
All right. All right, so there's our dog. Gravity's pulling the dog down, right? So here's our force of gravity. Negative 117.6 newtons. Named after person, not after tons. All right, so that's one of my forces. That's step one, mass and force of gravity. Step two, are there any explicitly described forces in the problem?
Yes.
Yes. Sally is pushing the dog down. So the dog's sitting there, and Sally's doing this. I don't know why. She is. Sally has dog problems. All right, so here we go. Force of Sally. 50 newtons, sorta. Negative. All right, so the dog is sitting here on the ground, just like my water bottle. She's pushing down on it. That's it. That's all we know explicitly. That's all we know, right? So now we got to think. So is this it? Are those the only forces? Can't be, because otherwise the dog would be moving down through the ground, right? All right. So what do we know about the dog? Not moving again. Therefore, my net force has got to be 0. What's preventing the dog from moving down through the floor? Normal force. How much? Well, exactly enough to make my net force 0. You need exactly enough enough normal force to make your downward forces cancel out, right? So what are we going to need? 167.6, right? Again, technically I did some algebra there. What I just did was, if normal force is x, I did x plus negative 50 plus negative 117 equals 0. Thanks, Adam. All right, are we good? So here's another example. Notice my normal force here does not equal gravity. Good? All right, any questions on E? All right, a quick side note. I don't think I put this example in here. There's an example on it. Well, here, let me do this one, and then I'll talk about it. All right. Oh, do I have 2 E's? Oh, that's embarrassing. All right, the 2 E's are not the same. So let's call this E and a half. E.5. I like E.5 better. Okay, so here's our dog again. Floppy ears, 1, 2, 3, 4 feet, floppy tail. Mass equals 12 kilograms. Gravity is pulling him down with 117.6 newtons. Those are, in fact, negative because they're pulling him down. So that's step one, mass and force of gravity. Am I going too quick? Step two, any explicitly given forces. Sally. Sally this time is lifting up on the dog with 50 newtons of force. Up this time instead of down. So again, we got to think. So, what do you guys think? Say it again. How do we know if the dog is moving or not? That's a really good question. That is exactly the next question you should ask. Well, what's Sally trying to do to the dog, Dave? Lift him up, right? With 50 newtons worth of force, right? What's working against her? Gravity. How much gravity is it? Negative 117. Is she going to succeed in lifting the dog? No, because to lift the dog, she would need more force than gravity, right? So what's the dog going to do? Just keep sitting there, right? She has not lifted the dog because 50 newtons is less than our force of gravity, ignoring negatives. So, right? So what does that mean? Since she hasn't lifted the dog, the acceleration is 0, and that means that my net force has got to be 0. So it's this. Imagine that this water bottle is really heavy. And I come along and I go, All right, all I'm doing is taking some of the weight off of the table, but I haven't succeeded in lifting it. The table's still supporting it a little bit, right? With enough force to make the net force 0. So I need to ensure that my normal force is big enough that if I add 50 and then subtract 117.6, I get 0. Okay, so let me do this explicitly once. I keep saying that I'm using the word explicit a lot today. I don't know why. That's the word of the day for no real reason. Go, brain. So let me actually do this. So look, net force is, what's the definition of net force, you guys? Sum of all the forces. So let's label them. We've got normal force, we've got Sally, we've got gravity. We know that our net force has got to be 0 because the dog's not moving. Normal force is what we're looking for. Force of Sally is 50. Force of gravity is negative 117.6. And solve that. So you get 0 equals Fn minus 67.6. So your normal force is 67.6 newtons. Does that make sense, you guys? So there's a lot of sort of, the math here is not difficult. It's the logic of realizing, oh, wait a minute, that's not going to lift the dog. Oh, that means the acceleration is going to be 0. Oh, that means the net force is 0. Oh, that means that the normal force has to be 67. Cool? All right. Any problems up through E.5? All right, F. We can probably skip this one. Yeah, we're going to skip this one. So you can take E.5 and make that F if you want. You know what? Maybe we do need to talk about it. All right. Sorry. Had you already X'd it out? Oh. How badly? All right. Well, you can just write a note in the margin. Check it out. Here's all that's going on in F. Gravity's pulling the raccoon. I don't know why I changed the dog to a raccoon. And then Sally lifts up with 117.6 newtons. Now, technically speaking, that's not enough to lift the raccoon, but what she's effectively done is taken all of the weight off of the floor. So there's no normal force. Right? So it's sort of like she did this and exerted just enough force that you can pull the table out, the floor out from under it, and, we're not lifting it because we don't have enough force to produce acceleration, but we do have enough force to sort of take all the weight off of the floor. So that's all that's going on there. Cool? Yeah.
If somebody lifted Sally then, would the net force on the raccoon change? Would it still be 117?
Indirectly, Sally would have to exert more force for that to happen. So, because the person lifting her is exerting a force on her, not a force on the raccoon. Now, if she wanted the dog to move up, or the raccoon to move up, then yeah, she would have to exert more force. So, have you guys ever noticed when you get into an elevator, when the elevator first starts moving up, you feel like you're heavier? Right? You feel that like, right? You actually sort of feel like you're being squished down into the floor, right? Okay, that's because the floor is now pushing up on your feet with extra force to cause you to accelerate. And then when you get to the top and you stop, you feel light for a minute, right? That's because you're decelerating, so the floor has to exert a little bit less force to sort of slow you down. So anyway, there's a homework problem about that. So All right, where are we at? Let's see. Oh, cool. So this time our dog. Oh, we're back to a dog again. Floppy ears. 1, 2, 3, 4 feet. Bushy tail. 12 kilograms. Gravity. All right, so this time Sally's going to lift up with a force of 150 newtons. So I'm excited. Why am I excited? Because she's going to actually lift the dog off of the ground, right? So, is there going to be a normal force? No. Remember, you guys, the normal force comes from the surface that the thing is sitting on. But this force is enough to lift the dog off of the ground. So since the dog's no longer touching the ground, there is no normal force. So no normal force because force of Sally is bigger than the force of gravity, so she lifts the dog off the ground. All right, so this is the first time this has happened. Every one of the problems we've done so far, what we've had is you've thought about it and gone, oh, it's not moving, so the acceleration is 0. Oh, that means the net force is 0. Oh, we can find our missing force. This time, there are no missing forces. Right? The only two forces are Sally lifting the dog and gravity pulling the dog down, right? So what should I do now? How?
You get net force.
Okay, there we go. We got to find our net force, right? So net force is the sum of all the forces. And for us, that's gravity and Sally. Those are the only two forces, right? There's no friction because the dog isn't sliding on anything. There's no normal force because the dog is off the ground. There's no air resistance because we always ignore air resistance. So that's it, right? So for us, it's negative 117.6 plus 150. That gives us, what, 32.4? And so now I can find my acceleration by doing net force over mass. So we've got 32.4 newtons acting on a 12 kilogram dog. So that's going to give you a 2.5 plus 0.2. So is that 2.7 meters per second squared? I did that in my head, so I should probably double check it. On 32.4 divided by 12. I'm the smartest man alive. All right. Questions on what we did then? All righty. When do we get out of here? 59? What's up? What did you say?
Well, H, that's
Is that how you spell gummy? I think it should be I, shouldn't it?
no, it doesn't want it. I think it depends. I think the eyes get in.
Okay, so here we go. So this one, Roy is lifting a box of gummy bears. So we've moved on from dogs, we're on to candy. So here's the floor. Here's the box of gummy bears. There are 8 kilograms. If you care, that's a little more than 16 pounds worth of gummy bears. 17 pounds of gummy bears. All right, so what's the first thing I should do? Put in my gravity. Force of gravity is 8 times 9.8. That's negative 78.4 newtons. All right. So we're going to lift it upward from rest with an acceleration of 4 meters a second squared. Oh, we know the acceleration. That's nice. What should I do with it? Find your net force. Net force is mass times acceleration. So that's 8 kilograms of gummy bears times an acceleration of 4 meters a second squared. We're looking at an acceleration of 32 newtons. I'm sorry, a net force of 32 newtons. So now we need to find out Roy's force. Do I need to worry about normal force here? No, why not? Because we've lifted it off of the floor, right? I probably shouldn't have even drawn the floor here because we knew he was lifting it off the floor, right? Okay. So net force is force of gravity plus force of Roy. So my net force is 32 newtons. My force of gravity is negative 78.4 newtons. Force of Roy is my unknown. Add 78.4 and you get, what, 110.4? Is that right? Equals my force of Roy. Make sense, you guys? Oh, I'm sorry. Thank you. No, the time is not irrelevant. I'm glad you asked that. So, remember I said at the beginning, oh, that's not what I wanted to happen. Remember I said at the beginning that if you knew anything about the velocity that you should include that in your drawing? Well, it says specifically to make a free body diagram after 3 seconds. So that's going to give us enough information. I know my acceleration. I know my net force. But I can also find my velocity, right? So let's see, Vf equals Vi plus At. So the starting velocity was 0. Acceleration was 4 meters a second squared. Time is 3 seconds. So the box is now moving at 12 meters a second. And so I can put that in my drawing as a little arrow over here and label it V equals 12 meters per second. Good. So the acceleration and net force are sort of an understood part of the free body diagram. And then if you're able to find out something about the velocity, you should include that. Cool? And I guess, now that I think about it, I guess I've been a little bit sloppy because we had a whole bunch of these where the thing wasn't moving. So we sort of knew the velocity, right? So really, all of those ones where the thing wasn't moving, I probably should have just written V equals 0 by them. So. Do we need to go back and do that, or are we okay? All right, everybody get up for H? Ouch. All right, piñata. A 5 kilogram piñata hangs from a rope tied to a tree. Make a free body diagram of the piñata. All right, what forces are acting on our piñata? He's 5 kilograms. So, what's the first force we should draw? Gravity. Negative 49 newtons. He's hanging from a rope tied to a tree. What else do we know? Sorry? He would have to be sitting on something to be a normal force. He's hanging from a tree. Well, the tree's not touching him. The rope is exerting a force. All right. When I said what else do we know, he's hanging there, so he's not moving, right? Therefore, my net force is 0. All right. Now, the thing holding him up is a rope. All right. Anytime you have a force exerted by something like a string or a rope or a chain or a cable or a sinewy tendon, we call that tension force. And it had to be 49 newtons because my net force was 0. All right. So in a lot of ways, it behaves similarly to normal force, except that it's, coming from, I don't know. All right, are we good? I will improve my unicorn then. All right, are we good? All right, Norm pushes a 160 kilogram pony to the left with a force of 960 newtons. Friction exerts 320 newtons. Make a free body diagram of the pony 2 seconds after Norm begins pushing. So, ground. Pony. All right, 160 kilograms of pony. All All right, gravity's pulling the pony down with a force of something. 1,568 newtons. All right, Norm pushes the pony to the left. Oh, shoot, left? Who wrote this problem? Normal force is negative 960 newtons, right? All right. Which way is friction going to go, you guys?
The other way.
The other way, right? Because it's going to resist the forward motion. All right, and then make a free body diagram of the pony 2 seconds after Norm begins pushing. What do you think? Christine said, don't you need a normal force? Tell me more. I agree with you, but I just want to make sure you... Okay, notice, even when something is moving horizontally, you can still have a normal force, right? It's this, look. Right now, the table's holding the water bottle up. It's still doing that, right? Okay, so that's all that's going on here. So how much normal force does it need to be, probably? 1,568, right? Enough to make it so that my up and down forces cancel. All right, so the way that we would express that is like this. We would say that the net force vertically is 0. Right? A little y just means vertically, right? Follow? All right. Now, does our net force horizontally equal 0? No. So our net force horizontally... Oh, darn it. Okay, so our net force then, technically speaking, the net force is the normal force plus gravity, but those cancel out, plus my, oh no, what did I do wrong? It's something very small.
Oh, I thought I was going to drop it.
What do we got? There's 2 FNs. That's not okay. We got to make this Norm. Make sure you don't use the same name for 2 forces, please. I actually have a friend named Norm, and that was why I wrote this, and it didn't occur to me until just this minute that that was going to be a conflict. All right, so here we go. Negative 960 newtons, 320 newtons. So you get negative, what, 640? All right, and so now you can find your acceleration, right? Well, no. All right. Pretty good? Yeah.
So if Fy wasn't 0, would the net force still be Fy plus Fx?
Yes, but you'd have to do vector addition. You'd use your components. You'd have a vertical component, a horizontal component, and then you'd find your hypotenuse. All right, let me plot. When do we get? Do we have 1 minute or 2?
1.
Wait.
I'm doing it real fast. And as a reward, let's do this. Tomorrow, I was going to give you guys a big homework tonight. Tell you what. Sorry. Why don't we do this? I think that we're going to do better if I give you guys time in class tomorrow to work on this. So here's what I'm going to do tomorrow. Listen, tell me if you think this is good. I know the bell's about to ring. I'm going to come in tomorrow with a detailed solution key for this, and I'll give you guys the hour to work on it. All right, but that means we won't have as much time to go over it, but you'll have all hour to work on it and ask me questions and stuff to class. Is that good?
Yeah.
All right, so no homework tonight. All right.
I'm gonna make this
No.
But I'll get
But if I go over it,
Oh, yeah.
I did that. Luckily, it was our first one, so I asked them if I could have it back some shots. And when I forgot, all the stress.
like better than a No. It's kind of weird. Like,
Frozen watch too.
Oh,